Let's review confidence intervals. So in the simplest case, I have the one sample model. So I could say I have a variable y, and the variable y has a mean mu, and assume normal distribution or some other distribution, and there's a sigma in there, right? Standard deviation. We could also write it directly rather than writing the distribution, writing it as y equals mu plus epsilon, where epsilon is the residual error. And so I'm pulling sort of the mean structure away from the error structure. And we're asking ourselves the question, what is a plausible range for mu? Now we have a sample of y's, and then you can compute a confidence interval with this formula. The confidence interval has a lower bound and an upper bound on the right, and they are the computation is the same except for this minus and plus in there. Let's see, annotate. Here is the minus and the plus. So other than that, the formulas are the same. Then we have this critical value here, and the critical value here and also here depends on the distribution of y bar. Now, given that we're interested in y bar, then assuming that we have a relatively large sample, we are really lucky. We are really lucky in the sense that the central limit theorem says that if y is large enough, then y bar, the average, is approximated by a normal distribution. So we can just take the value for c that corresponds to a normal distribution. And for the normal distribution, we actually remember, maybe, the value for a 95% confidence interval, and it's 1.96. Since we usually assume 95% confidence interval, or conversely, alpha equals 5%, this is a value that you will see many times and you may want to remember. Okay, so the interesting thing is this holds regardless of the distribution of y, right? Now, the sampling distribution of y bar. We have a probability mass, and the probability mass together, because the probabilities add to 1, right? So in the continuous case, the probability mass also adds to 1. And we're looking for a plausible range. And by that, we mean a confidence interval where most likely your average that you calculate from a sample falls most likely within that confidence interval. Right? So we divide that probability here into the confidence interval in the middle, where most times when you calculate an average, you are in that confidence interval. And then the tail regions, at the lower and the upper tail regions. So if you specify a 95% confidence interval, you are in here 95% of the time. Alpha is 5%. And half of those 5%, 2.5%, are here in the upper tail, and half of the 5% are in the lower tail. This whole thing is symmetric because of the normal distribution is also symmetric, right? So we have the critical value here, and here minus the critical value on the left-hand side. So here is the critical value, and here is minus the critical value. All right. Now, the correct statement about this is 95% of the time when we calculate a confidence interval in this way, the true mean will be in the confidence interval. There is a common incorrect statement that I will not read aloud, but as you can see down here, which is not correct. And the reason it's not correct, because this conditions on this particular confidence interval, whereas you get really what's happening is you get a different sample, you get a completely different confidence interval each time, right? So 95% confidence of the time, when you calculate a confidence interval, the true mean will be in that confidence interval. And it's a different one for each sample that you get. Okay, so we haven't really assumed a distribution so far. We just said, well, hopefully the sample is large, and then we know we have then y bar is going to be normally distributed. So suppose we explicitly assume normal distribution. And so I'm specifying epsilon is normally distributed with the zero mean because the mean is already out here in front in the mean structure. So zero mean and a standard deviation. Then we have seen in stat 231 that the sampling distribution is t with n-1 degrees of freedom. So specifically, we get this by subtracting the mean so that we have zero expectation here, and we are standardizing it to so that we have easier time here in the denominator. Okay, so how can you get a different distribution? By assumption, epsilon was normally distributed, right? And once epsilon, you add a constant, y is also normally distributed. That's just y, that's the theoretical distribution. The sampling distribution here refers to the mean, so to y bar, that's the sampling distribution. And it turns out that so it's a distribution when you take a sample, calculate the average, that's 1 point. You take another sample, calculate the average, it's another point, and so forth. And if you plot all these average, you're gonna get a distribution, and it's not gonna be this normal distribution, it's gonna be a t-distribution. And the t-distribution here is in green, has the property that it has heavier tails. Heavier tails means that there's more probability mass in the tail, both at the lower tail and the upper tail. There's still, everything is symmetric here above zero, right? And yes, so you're getting a different sample distribution, but because we know that for large samples, it needs to be normal, the t-distribution, as the sample size increases, needs to converge towards the normal. So as you, so the tails get less and less heavy until you reach the tail of the normal distribution. Now, what is large? When do you reach that? It happens very, very fast. So more or less, if the underlying normal distribution is right, more or less when you have 30 observations, then the distribution is, x bar is pretty much normal rather than t. Some people say 50, and there are minor differences, but 30 is good enough. So, and for the 95% confidence interval, we know for the normal distribution, the critical value is 1.96. For the t-distribution, that critical value is always larger, so say 2.5. And as the sample size increases, the critical value goes down until it reaches in the end in the limit, also 1.96. Here is the example, or an example, based on the 3 observations from earlier. The calculation, we are now assuming a normal distribution of the error. That means we get to use a t-distribution with 2 degrees of freedom. That degrees of freedom business. So it's n-1 degrees of freedom, right? We have 3 observations, there are 2 degrees of freedom. Why does this make sense? Well, when you compute the variation, you have to know mu in order to compute that, right? Because it's a y minus mu. And that means before you can compute a variation, you already have to have spent the equivalent of one observation, 1 degree of freedom, on computing the mean. And that's why when you have only one observation, you can compute a mean, but not a variance. If you have two observations, you can compute a mean and a variance, but just barely, right? And so you really only have one bit of piece of information to compute the variance. And so you basically lose one degree of freedom because you first have to compute the mean. You can theoretically prove that depending on whom you had for stat 231. You may have seen it or you may not have seen it. Doesn't matter. We just remember it's n minus 1. So I have my degrees of freedom. Here is the t-distribution with 2 degrees of freedom. The critical value is 4.3 from the computer or table. And then we have the standard error of y bar here. And that is 1 divided by square root of 3, because we have 3 observation and we have the square root of n down here, right? The standard deviation is 1, and here we have square root of n. So, and that gives some value. And if, we had a much larger number of observations, then instead of 4.3, we would have had 1.96 here. Okay. That ends this recording.